Hello, everybody, and welcome to another Geo-Institute live stream. We've got another amazing episode today of Books Rock, our quarterly publication series where you get to go behind the book with one of our esteemed ASCE authors. My name is Brad Keeler. I'm the director of the Geo-Institute, and we're thrilled to welcome you to, yes, another Geo-Institute live stream. If you don't know anything about the Geo-Institute, after you watch this amazing interview today, head over to geo-institute.org, and there you can find out all kinds of stuff about us, including that we're a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and I mean, we always do our best. I would feel guilty if you did not like what you saw. The fact that people keep coming back suggests that they do, so I'm just going to be okay with that. So if you like what you see, of course, click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. Of course, summer is drawing near, and really, is there a bad time to make your contribution to Geo-Institute student programs? But spring and summer are a great time to do it. And if you make the aforementioned contribution, you could own your very own Ralph Peck bobblehead. They look handsome on shelves. I mean, I guess you could carry it with you everywhere you went, but you probably wouldn't want to do that because it would break. All you have to do is go back to, again, geo-institute.org, click on Student Participation Fund, make your gift, and choose from the many thank you gifts that we have in exchange for your donation. 100% of it is tax deductible, and 100% goes to support students. So that is something that you want to do. Today, again, Books Rock, and as is the case when we have an episode of Books Rock, we bring in someone from the ASCE Publications Department who is going to tell you how amazing they are and give you a special thing that you don't want to miss. And so today, from the Pubs Department, it is Andrew Moore. Andrew, welcome. Thanks for being with us.
Thank you, Brad. And thank you for the Geo-Institute for hosting today's event, and for our speakers today to share their time and expertise. I'm going to share my screen really quickly and have a slide prepared with some information on today's featured book, as well as a discount. ASCE is the leading publisher of civil engineering knowledge, including books, standards, journals, and conference proceedings. Today, we'll be discussing frost action in soils, Fundamentals and Mitigation in a Changing Climate, a technical report developed by the Frozen Ground Committee and the Transportation and Infrastructure Committee of ASCE's Cold Region Engineering Division. This publication updates ASCE's foundational work on frost action, reflecting advances in technology and the evolving impacts of freeze-thaw cycles in a changing climate. For attendees today, we're offering a 10% discount on the book. Just use promo code ASCEPUB 2026 at checkout. You can scan the QR code on the screen or follow the link in the chat to learn more. And with that, I'll turn it back to Brad.
And now we get to our feature presentation. We've got a couple of Canadians for you today. From out west, BGC Engineering, our moderator today is Heather Brooks. And from the east, Université Laval, it is Guy Doré, one of our editors for the volume Frost Action in Soils. Thanks for doing this, guys. We're going to have a great time. Heather, take it away.
Hi, all. I'm very happy to be here moderating this session with my PhD advisor, Guy Doré from Université Laval. Just to do a quick introduction to Guy. Guy is an emeritus professor at Université Laval. His research has focused on pavement design and road design in cold regions environments, including in Nunavik in northern Quebec, particularly looking at roadways on permafrost or transportation infrastructure on permafrost. He's authored numerous journal articles, book chapters, and papers on these subjects. And not only was an editor, but was also an author of one of the chapters in the book that we're discussing today. So I'll turn it over to Guy.
Okay, thank you very much. I'm really pleased to be here today to talk about the book. So I'm going to give a short overview of the book. So I'm going to share my screen. Just give me a second.
And while Guy does that, I will remind everybody that there is the opportunity to ask questions of the two of us via the chat on the YouTube link. So feel free to use that. And Brad and company will make sure it gets to me to ask to Guy. Back to you, Guy.
Okay, so frost action in soil. So a book that was developed by a group of engineers that work on different chapters. Good teamwork. So essentially, what the book content is divided in three parts. First part is fundamental and climate context, includes an introduction and some historical background, mechanism of frost heave and thaw weakening, effect of frost heave and thaw weakening on roads and other structures, assessment of frost heave susceptibility, and frost action and climate change. The second part of the book is actually mitigation of frost action in pavements. One section on design principle, another one on pavement design methods in cold climate, and finally mitigation of frost action. Finally, the third section of the book includes a series of case study on analysis of frost mitigation under building perimeter slabs, frost susceptibility of existing pavement, and Allen Army Airfield frost heave. So in more details, the first chapter of the book is an introduction and some historical background written by Billy Connor and Sally Shoup. There's a brief overview of the history of scientific and engineering development on frost action and its implication for infrastructure design and performance. Second chapter is mechanism of frost heave and thaw weakening, written by Spencer Guthrie and Antti Nurmikulu. The chapter includes a description of heat flow in the ground, water transport, and heaving pressure created by frost action. Third chapter is effect of frost heave and thaw weakening on roads and other structure, written by Billy Connor, including a section on frost heave, another section on frost jacking, also discuss thaw weakening and frost action on shallow foundation. Fourth chapter, assessment of frost heave susceptibility, written by Spencer Guthrie and Antti Nurmikulu. Discussing frost index property, laboratory frost heave measurements, field frost heave measurements, and numerical modeling. And chapter 5, frost action and climate change, written by Travis Logan, Jean-Pascal Bilodeau, and Karen Henry, includes a discussion on North American climate change portrait of winter and frost action variable, relationship between climate and pavements, effect of reduced frost penetration, and increasing number of thawing event in the winter period. So that's the first section of the book. The second section of the book include design. So design principle, written by myself. So description of different principle and approach to deal with frost action in pavement design. The next chapter is pavement design methods in cold climate. So the chapter offers an overview of different methods used in United States, Canada, and Europe. It also presents conceptual mechanistic method to deal with frost action. The next chapter is mitigation of frost action, and includes discussion on frost heave mitigation and strengthened pavement structured for improved bearing capacity during spring thaw. Finally, we have a series of case studies. So the first case study is frost mitigation under a building perimeter slab, written by Daniel Overton, John Nelson, and Kuo Che Chow. And the article essentially describes how thermal modeling was used to design like a frost-resistant foundation for our building. The second case study is frost susceptibility of existing pavements, written by Denis Saint-Laurent and Gilles Briand. And the paper describes how the Quebec Ministry of Transportation does frost heave and profile measurement during winter to actually assess frost susceptibility of roads and underlying subgrade soil. So, and the third case study, written by Alan. The third case study called Island Army Airfield Frost Heave, written by Kevin Biella and Ariel Ellison and John Macastad. So this paper actually described how different ground investigation technique, including ground penetrating radar, were used to actually assess a frost heave problem at the airfield. Okay, so that's a quick overview of the book.
Yeah, thank you for that, Guy. Again, anybody who has any questions, feel free to put them in the YouTube chat link. But my first question for you, Guy, is, why is it so important to consider frost heave and frost action in your designs?
Well, simply because actually frost heave is a very important cause of infrastructure damage. If you look at the case of roads and pavements, it generally considered that like at least if you're in a cold environment where there's actually frost penetrating the ground, you typically have around 30% of damage caused by frost action on high volume road or high class roads, and typically around 70% of the damage caused by frost action on lower volume roads. So it's a significant cause of damage. It's also caused very important damage to structures and building, especially buildings that have a shallow foundation, but also buildings that have deep foundation, like piles that can be jacked by frost action. So it's an important cause of damage. So you need to worry about it and care about it.
Yeah, in those pavement environments, what kind of damage are you tend to see and talk about when it comes to that percentage?
Well, it typically during winter there'll be frost heave, and that actually causes excessive displacement and strains in the structure. So if you're looking at pavements, you typically have frost heave that can reach, in some case, 200 millimeter, 250 millimeter in severe case. So it's extremely important strains for the structures. And the other thing is that frost heave is rarely uniform. It's usually variable. So it creates what we call differential frost heave, which is actually the main source of the problem, because if you can imagine a structure heaving uniformly, it wouldn't be that much of a damage. But if it heaves unevenly, then it creates all sorts of problems. So, of course, the other aspect of the problem is the frost heave will create condition in the soil where you're going to get drastic change in soil property during spring thaw. So actually, your bearing capacity is going to be severely affected. Your shear strength, most soil property will be strongly affected by spring thaw. And the more frost heave you get in the winter, the more bearing capacity or shear strength loss you'll get in the spring.
Okay. So, frost heave processes, generally form ice lenses that are perpendicular to the direction of freezing. So if you have a situation where you have freezing from different directions, how would you consider that within the frost heave design?
Yeah, well, that's, as you just said, frost penetration, frost heave will essentially occur perpendicular to the surface of the ground that's affected by the frost. So in most practical cases, like for pavement, typically we consider vertical freezing and vertical eaving. And that's, I would say, the simple case. But for structures like, for embankments where you have like a flat surface and slopes on the side, or for a structure like retaining wall, for instance, it can create some severe problem because frost again will evolve perpendicular to the surface.
Yeah.
So looking at a retaining wall, the frost will penetrate through the wall and then push against the wall. So of course it creates some severe problem with the stability of the wall if it's not accounted for in the design. And the same thing for an embankment. Things we never really consider in a design is that your slope will create a situation where frost will penetrate perpendicular to the slope, and eave will push against the slope. So if you have, again, severe case of frost eave, what you can get is what we call embankment spreading. So the slope are being pushed outward, and that creates embankment spreading. Yeah.
So when you're looking at the frost heave problem, what are the key elements or lab tests that you need to use to determine frost susceptibility, and what indications would make you suspect that frost heave might be a problem at the site?
Okay, well, first point you said about key elements for to consider for frost heave. I guess, well, you probably all heard about the three conditions for frost heave, which is frost susceptibility, sustained cold temperature, and then moisture available. So these are the three main factor causing frost heave. So of course, the risk has to be assessed on the basis of those three actions. So again, so if you have cold conditions that are persistent, of course, this would be the main driver for the problem. Then if your soil is frost susceptible, and that's a key element, then the amount of frost you will get, of course, is directly proportional to the susceptibility of the soil. And then, of course, you need to understand that frost susceptibility, and you also need to understand the other point I was looking for is the variability of the frost susceptibility, because again, if you have uneven frost heave, you have a much more severe problem than if you have uniform frost heave. The third aspect is the moisture. Of course, you need to have moisture available, and that's of course definitely a problem, because it's moisture migration which will cause frost heave and will again create stress and strain on the structure. And of course, you have to look at all of these. The second point you were mentioning, how do you characterize that? Well, the thing that's important to consider is we need to start thinking about frost susceptibility. We have to start using mechanistic index to measure frost susceptibility. Now, we in the past, essentially, we've used mostly rules of thumbs, like based on gradation or empirical information. If you have that much fine content, and it makes it frost susceptible. But frost susceptibility is the same type of property. Like it has the same meaning for frost heave as the resilient modulus as for mechanical performance or repavement. So frost susceptibility is the response of the material to the stress, which is actually the cold temperature. So using a mechanistic index, for instance, like the segregation potential, is widely used in some countries. Other country will use frost heave rate in a freezing cell as the mechanistic index. So if you use that, you can relate the severity of the cold climate to the response of the material, which is frost heave. So that I guess we should aim at using that kind of index to actually characterize frost susceptibility. Also, we need to consider using the same approach an ASCE is using for material characterization for like resin modulus. We need to use I have so much problem with that word, hierarchical approach. Does that make sense?
Yeah.
Translated in English. Good. So yeah. So level one is being the most accurate or most detailed characterization, and you use level one when you're dealing with high class highway or sensitive building. So you'd use then the way to characterize would be using a freezing test in a freezing cell, and actually determine the frost heave, like the segregation potential or the frost heave rate. Level two would be correlation with index property or gradation, and again relate using correlation to relate those parameters to the segregation potential or frost heave rate. Again, keeping in mind that if you use the mechanistic index, then you can actually optimize using that, while you cannot with the frost susceptibility like F1 or F2 or F3. You cannot optimize using that. And level three would be a typical value of segregation potential or frost heave rate associated with soil classification, for example. And level three would be used for lower level, lower class roads or low traffic roads, where you can tolerate more risk and more damage.
So one of the things I think we need to back up and maybe define for this audience is, what is segregation potential? Because I don't know if that's used widely in the US. I know it's widely used in Canada because Jean-Marie created it, and it is, a very Canadian adaptation or adoption. But maybe for this audience, we should spend a minute and define what segregation potential is.
Yes, the segregation potential is really an analog to the resilient modulus. So resilient modulus is the ratio of the slope of the relationship between stress and strain. So stress applied to the material and how the material deforms, and the slope is the resilient modulus. Same thing with the segregation potential is the slope between the cold temperature, the intensity of cold temperature, and the rate of heaving, the heaving rate. Now, the intensity of the cold temperature is the thermal gradient between between the surface and the freezing front. So that actually it's the thermal gradient at the freezing front, which you can actually which actually is roughly equal to the gradient between the surface and the freezing front. So that's the stress, and the strain is the rate of heaving. The segregation potential is the slope of the relationship between the two. So you get that from a freezing test. So you actually submit the sample to a thermal gradient, and then you monitor the heaving of the surface. So, and the heaving rate is the higher the segregation potential, the higher the heaving rate will be for a given thermal gradient. So again, it allows you to relate the stress and the resulting strain. So that allows you to actually do a mechanistic analysis of frost action. And
do a prediction of how much frost heave you might get based on the soil conditions you have in a typical winter. So you actually can have an estimate of that differential movements, correct?
Correct. Yeah. Based on you use the freezing index will tell you will give you an average surface condition, and from that, knowing the depth of frost penetration, you can estimate your thermal gradient. And if you know the segregation potential and use that average thermal gradient, then you can actually predict the amount of frost heave.
Yeah. A lot of places in the US use a lot of salt to help mitigate snow and ice on their road systems. Does that salt maybe influence the chemistry of the pore water and the frost susceptibility in any way?
It does, yes. Well, it does in two ways. First way is, of course, it depresses the freezing point. So, of course, that changes a little bit the dynamic because freezing point is going to be lower than 0 degrees Celsius. So, and the other thing that it does is actually if you're freezing saline soils, you're actually, the freezing process will expel the salt in front of the freezing front. So you're creating a zone of high concentration, high concentration of salt in the pore water in front of the freezing front, below the freezing front. So what that does is it creates an osmotic gradient that will actually oppose the cryosuction grade that actually feeds the freezing process. So actually, it reduces the frost action. Yes.
Oh, interesting. I guess now that we've kind of talked through a little bit of the process of frost heave, what are some typical mitigation measures to deal with frost heave?
Well, again, if you consider the problem being caused by three main factors: cold temperature, frost susceptibility, and moisture, like any measure that you can take that reduces one of these factors will help. Okay, so of course, cold temperature, there's not much we can do about it, except that we can actually reduce the effect of cold temperature to the ground by using insulation. And using insulation layers in pavement is probably the most effective technique to reduce frost action. So one of the best mitigation technique. We can also work on reducing the frost susceptibility of the ground. That can be done by removing and replacing frost susceptible soil. So it's probably the most drastic way to resolve the problem. Also very expensive, but also we can use chemical treatment of the soil to reduce the frost susceptibility. And finally, we can use drainage, because drainage will reduce the availability of moisture. But we have to be careful, because drainage is not in a case where you have severe frost and deep frost, it will not help that much, because actually the frost front can draw water from 40 meters below. It's very powerful, and it will draw the water up. But of course, the more distance you have to pump the water, like it reduces, of course, your hydraulic gradient and reduce frost action. So good drainage will help, but it will not solve the problem. Rarely.
Yeah. I mean, most of the time we look at this as very much a vertical problem, but there is the risk that, water sources from lateral drainage could impact your frost heave.
Yeah, absolutely.
Yeah, that's definitely something that I keep in mind when I'm looking at stuff like this.
And okay.
Oh, go ahead.
Yeah, I was going to say that the other aspect is thaw weakening. So there's also mitigation also, and try to mitigate thaw weakening, that if you accept the frost heave in the winter, you can mitigate thaw weakening by strengthening your pavement. So typically building a stronger pavement to resist thaw weakening. Yeah.
Speaking of thaw weakening, what does that process look like, and why does frost heave impact the thaw weakening or create that problem to start with?
Yeah, exactly. There's three main factors that will influence thaw weakening. The first one is the water accumulated by frost action. So frost heave will actually create a situation where you have a high potential for thaw weakening if you accumulate lots of excess water
Yeah.
water in excess of the natural porosity of the soil in taut condition. So if frost heave again will accumulate the moisture and create a situation where there's high potential for weakening. Second important point is the rate at which thaw will progress in your pavement. If you have a very warm spring, thaw will progress very rapidly and release very rapidly the water that's in excess in your system. And the third factor is how effectively the soil can drain that excess water. So if you essentially for an exact same pavement, two consecutive spring you can have one spring lose half of your bearing capacity, and the next spring have 10% reduction in your bearing capacity because of the combination of climatic factors, like frost heave accumulated in the winter, and the way that that excess water is released and drained in the spring.
Yeah, so with that thaw weakening system, we talk a lot about the numbers of freeze-thaw cycles in pavement design or in the design of these structures. How does the number of those cycles impact the amount of thaw weakening you see?
Well, perhaps it would be good to back up a little bit here, because when your pavement is thawing, there's two critical periods. The first critical period is early in the spring, when actually you tar your pavement foundation, or your base granular material is thawing, and typically early in the season that occurs at the center of the pavement, and it's still frozen at the edge of the pavement because of snow accumulation and ice form on the edge of the pavement. So thawing is happening at the center of the embankment, and the water is trapped there.
Yeah.
And then you have a strong weakening of the granular material because the material is saturated. And during that period, you can have accelerated fatigue cracking and accelerated permanent deformation. Okay. If the other critical period is when thaw reaches the subgrade material, ice-rich material, and then you'll have a general weakening of the pavement. But coming back to the first situation, if you have several freeze-thaw cycle in a year, every time you thaw the top part of the pavement, you're creating a situation where you can damage significantly your pavement. So several freeze-thaw cycle will cause lots of damage to pavements.
We're kind of going to switch infrastructures for a second, because we've got a question from the audience, and that is, can you please reflect on different laboratory testing measures done to assess frost susceptibility of soils and characterize the associated frost jacking force? And they're specifically interested in driven steel H piles.
I guess this essentially the point I made a bit earlier. Now, that would be a case where you need to have a detailed characterization of frost susceptibility. If you run like a frost heave test in a frost cell, you will get very good information on frost heave, frost susceptibility of soil. Now, the load you need to apply to actually annihilate that frost heave force is very high. So that need to be calculated. Now, there's in the theory, like the segregation potential theory, there's equation where you can use the load and see how it's going to affect your frost heave. But yeah, for something like that, you need a detailed test to understand the frost susceptibility of your soil. Of course, then if you're thinking of a pile, an ad-freeze force, then you're getting into something a little bit more complicated, because you need to understand the creep that's going to happen between your pile and the frozen ground beside. And again, that's relatively well described in foundation theories, foundation manuals. So, but you need to have good information on the frost susceptibility of your soil. Yeah.
In the situation where you might have a high frost susceptibility material and frost jacking is quite a risk, would you alter your pile choice to make sure you have slightly less surface area that the frost heave can act on?
Well, I'm not specifically an expert in pile design, but it's very well described in the pile design for frost condition. It's well explained for permafrost condition, and it's also well explained in the seasonal frost condition. You have to calculate the force that are going to be acting on your pile due to frost heave, and you have to calculate the resistance of your pile to that force. So it's a calculation that needs to be done to have to answer to understand your problem.
Yeah. Well, I hope that answers your question, audience member. Maybe we'll just kind of switch things up a little further and talk a little bit about how this book focuses a lot on frost action in soils. But geotechnical engineers, we work a lot in rock. How does frost action affect rock, and how do the processes that we've talked about change a little bit in thinking about rocks versus soil?
I'm not fully comfortable to answer that question, because I'm not I've never worked in a rock environment.
Yeah.
But I believe that actually I don't believe that frost segregation heaving is happening in bedrock.
Yeah.
Perhaps somebody will say that I'm wrong, and that's possible, but I don't believe it's a main concern. But the main concern would be actually expansion during phase change. So actually, when you have a crack in a rock slope, and it's actually a fractured environment, so you have actually water infiltrating in cracks and creating a pressure that in some case can actually detach a block and create an incident where a block would fall on the road or something like that. So my understanding of the problem is mainly due to actually volume increase due to phase change. But again, I might be wrong, and I've not had time to actually document that specific case.
Yeah, I think it's something that's interesting to focus on the mechanics of the soils and how the grain and the capillary action interacts. One of the things that you and I are most familiar with is frost action and permafrost environments. What should the audience know about designing infrastructure in those environments?
In permafrost environment?
Yeah, or specifically related to the frost processes and how they're slightly different when you're looking at a confined active layer situation.
Well, that's exactly what actually the fact that you have a confined active layer is the key aspect. There's the frost action is exacerbated by actually, first of all, the presence of two freezing front. Work like evolving one toward the other, and second, by having captive water in that layer that can sometimes be under artesian pressure because of like slope terrain or something like that, and that pressure in the water will actually enhance quite significantly the frost action, because again it's a question of hydraulic gradient. So if you put pressure, if you're working in a pressurized environment, you're going to get much more efficient frost heaving.
Yeah, thanks for that. We've got a follow-up question from the audience about how basically surface vegetation or surface condition might help or reduce frost heave potential.
That's a good question. It actually might play a role in different way. It might play a role in terms of it might affect the way frost would evolve in the ground, because it is well documented that, for instance, if you have vegetation and an organic layer, this will actually impede a little bit frost penetration because of thermal conductivity, and also because of the moisture retained in the organic material and in the roots and everything. That will actually will generate latent heat that need to be evacuated before frost can process deeper in the ground. So that is one way that it can help. The other way it can help is that actually it sucks water out of the ground. So actually it possibly reduces the amount of water available in the ground to feed segregation freezing.
Nice. Since the publication of this book in, I think, 2019, is there anything that has advanced in the field that the audience should know about that's not in the book?
Well, I think that the book has actually looked into the basic concept, the current practice. Of course, the state of the knowledge is always a bit in front of the state of the practice.
Yeah.
And yes, there's things that have been that has evolved since the publication of the book. I think there's still lots of people working on trying to better understand and better model frost action. And I know that there's a lot of work being done using numerical modeling to do that, and coupling like the thermal behavior with the hydraulic, like a moving water in the system, and coming up with models that can predict frost action. So that has evolved quite a bit since the book, but the book doesn't go into that kind of detail anyway. So this is actually research, and it eventually feeds into the practice. In terms of practice, there is currently some evolution towards using more and more mechanistic, empirical principle and models to actually do pavement design for frost action. There's probably a few country and state that are a bit ahead of the others in doing that, like Finland, Sweden, Quebec is doing quite a bit. Is also doing a good job in doing that. So they're actually using segregation potential to predict frost heave and working with an allowable frost heave concept. So actually you can actually do something that gets pretty close to doing optimization. I think there's still something missing. It's probably still the prediction of damage, which is not well actually integrated into those methods, but it's evolving slowly. Frost susceptibility characterization, again, developing models so you can develop reliable assessment of frost susceptibility based on easy to do tests, like using index property and gradation, and relate that to a frost heave rate or segregation potential, for instance. So there's been progress in that field. And the other aspect also that has improved a bit is working in terms of because typically in pavement we work on the long-term behavior of the road. But working specifically with winter roughness is something that has developed a little bit, and that's something promising because we need also to control the condition of pavement during winter. So frosty will create roughness in the winter, and you should and agencies should be able to control that as well. Not only long-term performance, but also seasonal performance. So that's something that has evolved a little bit in lately.
Just talking to the audience for a second, this is last call for questions. I've got 2 more for Guy. If there are any others that you would like to ask, please put them in the chat and I will add them to my list. But one of my questions at the moment is, how is climate change altering frost heave risk, and how should engineers think about that?
Well, yeah, climate change will affect winter behavior of pavements. It will help in some ways and will be detrimental in other ways.
Yeah.
Of course, winters are getting warmer, so there's good chances that there's going to be less frost penetration and less frosty because of that in the future. So less damage caused by deep freeze of the pavement.
Yeah.
On the other hand, there will be more. Well, there will likely be more precipitation, and frequent and abundant precipitation in the fall might create a situation where frost is more effective, and actually frost heave is more even with a warmer winter, there's more frosty. There could be more frosty if there's more water available.
Yeah. And
thirdly, the other problem is actually related to what you mentioned earlier, which is the freeze-thaw cycle during winters.
Yeah.
Okay, the more freeze-thaw cycle we're going to get, the more damage we're going to get in the surface of the pavement during winter, because of the weakening in that surface layer, which is extremely susceptible to loading, traffic loading. And very often, a winter freeze-thaw cycle will typically generate very shallow thaw, which doesn't trigger load bands.
Yeah.
So you will get full traffic in condition where your pavement is vulnerable. So that's probably the main risk associated with climate change.
Yeah, that makes sense. So what do you think are the key takeaways for the audience, either from the book or just on what to think about when it comes to frost heave in general?
Well, I hope that the book and this event now is actually good for the awareness of the importance of considering frost action in the design of engineering structures. There's lots of good elements in the book to actually raise the awareness, and I think that's one of the benefits that people are going to get by reading the book. And as I also think, and that's not, the book hasn't made it to that point yet, but again, I think the book will raise the awareness of the importance of using mechanistic method instead of empirical methods and rules of thumb to actually design pavement for frost action.
Oh, that sounds good. We've got one last question from the audience. Could you discuss a bit about retaining walls and frost heave lateral forces? Have you encountered field conditions where retaining walls have had such damage?
I know, I'm more on the academic side, so I don't very often design a retaining wall and have actually case history of a retaining wall that failed. But I'm sure if the retaining wall was not properly designed, I'm sure there's quite a bit of failure that happened because of that. Of course, you have to again there's not much I could say about what needs to be done, but you need to have your wall need to be anchored in such a way that the anchors are going to be resisting the frost heave forces. And of course, there's a draining layer behind the wall that's extremely important actually to keep the condition relatively dry behind the wall.
That I think is the biggest concern I tend to have when it comes to retaining walls in cold regions is where do you place your drainage? Because most of the time we try and put it right behind the face of the wall. But that's where it's most vulnerable to being frozen with cold regions. So sometimes, placing it a little bit further back, or at least thinking a little bit about having some redundancy in those drainage systems might be important. And then one last question, which is, how do you properly characterize frost penetration depth? Like what methods?
Well, there's several models that allows you to do that. There's like numerical model, not numerical, but an analytical model like the Bergen model, for instance, that will allow you to predict frost depth. The segregation potential, if you use that into the calculation of frost depth, that will help you a lot because actually take it into consideration the migration of water during frost penetration. And so there's Conrad has published a model where he used the segregation potential in combination with the Stefan equation and come up with a very good model that predict very effectively the frost depth. The other also possibility is with there's several numerical model out there now that allows you to predict frost depth, like including like temp W, for instance, that can allow you to actually model your system and predict frost depth because it accounts for heat movement in the ground. It doesn't account for water movement in the ground, but it accounts for latent heat when the soil freezes. So you can have a pretty good prediction with those models. So of course, when we're like designing, we're predicting. So we're not, but of course, any models that you like to use, you need to calibrate it with field observation, because whether it is the Bergen equation or temp W, that remains theory. So if you don't calibrate your theory with real observation, you'll always be in the virtual world and not in the real world.
When it comes to calculating, the frost penetration depth, one of the things that I always think about is, what indices should I be using? Do you use a design indice? Do you use an average air freezing index? Like, for that kind of design question, which climate variables do you think we should be using?
Well, whether you use an indice or like a more detailed index, you also need to actually try to simulate a very the variation in that index. Like you need to, and that's something you've been doing in your PhD is actually try to iterate using the standard deviation of each one of your input parameters, so you actually have you predict a typical frost depth, but also a possibility of a range of possible frost depth, and then you can use that using you can use that in a reliability analysis. And if you need to have you need to have a low risk of problem caused by frost depth, you'll use a high reliability value in your range of predicted frost depth and frost heave. So again, all these parameters have a variability, and you need to again do simulation across all these variations to have a detailed answer of frost heave and frost depth.
Yeah, I agree with you there. I think that wraps up all of our questions today. I want to thank you, Guy, and thank you all in the audience for participating with us. I'll turn it back over to Brad for some final thoughts. And thank you all for attending.
It was fantastic, guys. Great job today. Thanks, Heather, for a great job moderating, and Guy for fielding all the questions and giving us a breakdown of frost action in soils. Technical knowledge is one thing. I think we should have everybody walk away from this today with a little something else. Guy, can you tell everybody in the audience how you would say the term frost heave in French?
Soulèvement au gel.
That is amazing. So I'll put that down in the comments so that people can see the spelling and everything, and learn a little bit of geotech in a foreign language maybe for them. That's excellent. Thank you for doing that. For all of our viewers, if you liked what you saw, and you're here at the end, so you probably did, click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. I want to say a special thank you to everybody who did ask questions today. It's fantastic that we have people come to our live streams. What really makes them vibrant and interactive is when people ask questions. So we really do appreciate you for putting those questions in the chat today, and hopefully you got a little more out of it because of that. Next live stream is going to be next Thursday, 9 days away. It's a bonus GeoStrata Extra. Everybody knows we do one of those for every single article or every single issue of the magazine. We're doing a second one this time because the latest issue on coastal geotechnics was just that good. So we'll have authors Monica Chaston and Brian Harris here to talk about designing coastal wetlands. You don't want to miss out on that. You can, of course, register for free on our Eventbrite page. And the week after that, hold on to your hats. It's Geopalooza. 11 straight days of brand new content. You never know what you're going to get. You can register for all the live streams that will be part of Geopalooza on the Eventbrite page, and keep watching our social media and geo-institute.org for announcements about other things that are going to be included in this amazing festival of geotechnical action. So we hope to see everybody at a future GI live stream. Our producer today was Aurora Flieger, and we will see everybody really soon.